Well, Patrick, thank you very much for having me. And I apologize that I didn't make it last year. Some of you might have noticed that I have a slightly strange accent. I'm originally from South Africa, but I find that I'm not alone. There were a couple other people from South Africa. South Africans have got some really strange personality traits. We tend to be a little bit pessimistic on one hand, but we tend to be optimistic that we can fix anything with baling wire, okay? So this goes with autopilots and UAVs. So I've been working in the ag sector with UAVs since about 2006 formally. The first time I saw a UAV used in ag was back in South Africa in 2003 with a large multinational agricultural company. We're using a gas helicopter with a 35mm film camera. So for some of you that are new to this field, you're thinking that we're just starting off. People have been putting cameras on radio-controlled planes for a long time. So we're going to talk about agricultural usage. And if I can get Patrick. There we go. Right, so 2006 until 2013, my telephone did not ring once, okay? What happened in 2013 that changed the industry? This very well-known graph that AUVSI put out that said in the next 10 years, drones or UAVs for agriculture is going to be a $180 million business, all right? The phone went crazy, and people are enamored with the technology for ag. We want to get drones for agriculture, all right? But there are a couple of critical things. People are not thinking about this technology critically enough in the agricultural space. They think they can go out and start a UAV company or a UAV service company, and I would urge them to think about these things, these questions that I'm going to ask before they go out and do that. Patrick, this is not working. Oh, there we go. Okay. All right. This slide is a little bit hard to see, but what it represents is a section, 640 acres, corn, soybeans, etc., in the Midwest. There are about 160 million acres of corn and soybeans grown in the Corn Belt. All of this is potential, okay, data that needs to be captured in some way. So over here we can see the orange line represents the 640 acres, and the quarter section, 160 acres, is represented by the blue line. And I want you to think about this as we go through the slides. I don't know if you can see that little red dot in the middle. That little red dot is that 640 acres in a number of counties in the Midwest. And here we have the three I's: Iowa, Illinois, Indiana, the largest corn and soybean producers in the world. All right, and sorry, 84 million acres of corn, 74 million acres of soybeans. This is, our fields are ripe for using some kind of technology to image them during the season. Visual imagery, near-infrared imagery. And how are we going to do this? Well, the logical step is to remove the pilot and remove the aircraft and use UAVs. Now the question is, what type of UAVs? Small UAS, large UAS, what is going to be commercially viable, what is going to be practical? Farmers are very practical people. Don't stand in front of an audience of farmers with a John Deere hat on and expect them to believe that you work in ag, okay? So, some typical ag UAVs that are out there. We're not talking hundreds of these systems. The FAA would like to think that they're hundreds. We're probably talking about thousands of these systems being employed by farmers right now, because they don't believe that they have to report to the FAA. Okay, they're out there flying right now. So they're typical ag UAVs. DJI Phantom, 3D Robotics, Precision Hawk, and the EB from SensiFly, and a number of others that are out there. So what can you do with these legally today? I don't know if everybody can see this slide. Let's talk about FAA regulations and safety. How much ground area can I cover with a small UAS and pretend to comply with the FAA? That means keeping my UAV within visual line of sight. So here we can see the smallest rotary wing systems. You can't push a rotary wing system out more than 1/4 of a mile and actually see it. It starts to disappear already. Then we go up a little bit. Okay, a small fixed wing, another 1/4 of a mile. So I can only get, or probably capture imagery-wise, 160 acres per flight and keep that machine in visual line of sight. Slightly bigger UAV, if I'm standing in the middle of the 640 acres, we can pretend to see it. Okay, pretend. If we've got a spotter out there with a two-way radio, maybe we can actually keep the thing under observation. So right now, if you want to fly and stay within visual line of sight, the maximum you can do with a rather large UAS system is 640 acres per flight. Now, if your UAV doesn't come with a near-infrared camera and a visual camera, that means that you're flying twice, okay? So how much service can I provide per day? How many flights can I go out and do? Now, this is something that the industry is not talking about. Other than producing pretty pictures that the farmer is going to put on a fridge, okay, this requires ground control. We need to put ground survey points out to actually build accurate maps. Now remember, farmers have been using RTK GPS for years. This gives them inch accuracy. All right, now if we don't have this data, you could have floating errors, and I'm going to talk about this later, of up to 60 feet. That's no good to a farmer. So you need to put, right now, you need to put in ground control until technical problems have been solved. So you're running around in the field and you have to have a guy up there on a quad runner, okay, and find some way to get your ground control into the middle of 1,000 acres of corn. And we'll see a picture of 1,000 acres. So the next thing is efficiencies of scale. That 160 million acres out in the Midwest, I'm not even talking about California's high-value crops. How are we going to capture this data? What's going to be more efficient? Flocks of small UAS being operated in their thousands, or very large UAV systems? Which is more efficient? Which is cheaper? Okay, because right now, you can probably buy a second-hand Cessna for $60,000, camera system for another $30,000, and you can go to work providing imagery. But then we look a few years down the line, and what is more efficient? Solving the problems that we have today with satellite technology and capturing this information using satellite. So what I'm telling you is that the window in agriculture for data collection, we've got a window, all right? Maybe it's 10 years, maybe it's 15 years, but eventually the most economical way to actually capture this data is going to be satellite. Some of you might not like that, but it's probably what's going to happen. A farmer will stand in a field with his cell phone and order that imagery, and it'll be downloaded to his cell phone. That's the vision from a satellite, not from a UAV. Right, there's a lot of misconceptions out there. Some of you, this might be apparent, but others not. The difference between resolution and ground accuracy. A lot of manufacturers are touting resolution, and they bandy numbers about like 2.8 centimeter resolution, sub-inch resolution. That's the pixel size on the ground. Okay, now you have to ask yourself, where is that pixel in time and space? Okay, so over here, we've got 2.8 centimeter resolution, and I don't know if it's clear on this slide. You see the little yellow stripe on the ground? That is a 1 centimeter ruler. Now what this means is that theoretically, we can identify an individual corn plant in a field. Now the farmer needs actionable data. He needs to know where that corn plant is. So the next problem. Accuracy. Lots of flight planning tools out there using Google Earth, okay, as a base layer. What's the problem with Google Earth? It's 15 to 20 feet out at any one time. And if you don't have differential GPS okay, on your UAV, you've got no way to correct for this without putting in ground control points. So you're starting off with an error of 15 to 20 feet to begin with. Then you go out there and you actually gather this data. And then what do you have to do? You have to process all these images, hundreds, if not thousands of images. And we have to correct for things like lens distortion, topographical distortions, camera attitude, and then we have to georeference it. And that's all reliant on ground control. Okay, at a minimum, we have to have 5 points. 4 corners, 1 in the middle. All right, now, the algorithms are better as they get closer towards the ground control points. But as you move away from ground control points, this creeping error increases. Now remember, farmers are used to having this sub-inch or sub-foot accuracy. All right, and a sprayer's boom is only 15 feet across. And he might have multiple hybrids of corn or soybeans in rows. He has to tell the difference between one row and another. And if we can't deliver that, we haven't done anything. And nobody yet has told me how you get ground control into that 1,000 acres in the middle of the season. So, Patrick, I've left your audience with some things to think about, okay, if they're getting into the UAV business. Any questions?
Now's your chance to ask somebody who's been doing it.
Okay. Yes, sir.
Do you use double band GPS in the drones?
If you're talking about differential GPS or RTK GPS, we have the capability to do that. No, it raises the price of the UAV unit considerably. To my knowledge, there's only one company right now that is offering a low-cost, okay, RTK GPS solution, and it's literally been released in the last couple of weeks. Yeah, yes, sir.
Hi, Bo from Aurora. I had a question for you about some of the methods that are using. It's a little technical, but I don't know if you've looked into some of these things or discussed it. A lot of what is out there right now is using GPS in kind of an absolute forum. But what I've seen coming up recently is a lot of localized ability to gain situational awareness using things like optical flow, in which case you're essentially mapping out the area in relative terms where you set a single point and then it's able to calculate distances and ranges over that whole area. They do that a lot with like the LiDAR stuff and so forth to get a map that continuously meshes as it grows. Have you seen anything like that?
Right. There are methods like this, but at some point in time you need an absolute position to correct everything. And if the farmer doesn't have that absolute position, you've got a problem. And so, for example, with RTK GPS, there are various networks around America that are providing these RTK corrections. If you don't have access to one of those networks, you're looking at a situation where you have to put down an RTK base station, and you'll have to let it cook in the field for 24 hours to generate a solution. So your really simple, convenient UAV flight now becomes a process of camping out while you wait for the solution to be generated, and then go and fly the next day. So.
Thank you, Rory. I'm Paul from Mapbox. Really enjoyed your presentation. I'm wondering if you can speak a little bit on the distribution side. So once you've gone out and you've flown these missions for farmers, how are you delivering the imagery? What's the best way to connect with them and
hard copy.
Hard copy.
Hard copy.
Physical media.
Yep. Okay, some farmers, it depends on the farmer. There are growers out there that are using pre-existing services to manage their GIS requirements. And this is another thing. I've been speaking to a lot of people that they're getting into the agricultural data analysis business. What they fail to realize is that people have been in the agricultural data analysis business for 30 years, and they're 90 million acres ahead of you. So rather team up with them. But at the lowest level, farmers walk around with a binder, okay, with near-infrared imagery from last year, and they try and make a decision about this year. Sometimes that image is on a server in the cloud somewhere.